Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today, we're going to look at a screencast called Basic Changes, or Observing Patterns that Allow for a Change of Base. This is in reference to Unit 1, Topic 3, where students are asked to learn a change of base to solve exponential equations. There's a couple of key ideas and a couple of great extension possibilities with this particular topic. First, the key ideas. There are patterns that allow us to change the base of exponential expressions so that we may equate them. Once bases are equal, the exponents can be equated. The equation form from equating the exponents will always be linear in Unit 1, Topic 3. The change of base generates coefficients used to solve the resulting linear equations. There's also some good extension possibilities. Using fractional powers to equate bases. Also, that the equation resulting from the exponents might have no solutions, one solution, or infinitely many solutions. Those two extension possibilities are not assessed in any of our tests. However, they are great extension possibilities within any classroom. Helpful skills. At this point, students have already learned a number of skills essential for this unit. The first is proportional reasoning with integers. Students have engaged in that learning in Math 6, Math 7, or IM. They've also learned that exponents represent the number of products of that base. They've learned that in Math 6 and IM, or Math 8. Another skill that they've already learned at this point is to solve linear equations in the form a times the quantity, bx plus c, equals p times the quantity, qx plus r. Students have learned this in Math 7 and IM, or Math 8. It's reviewed in Unit 1, Topic 1 of Algebra 1. They've also reviewed the power of powers rule, the meaning of negative exponents, and the zero power of numbers. This is done in IM and Math 8. While there are numerous other rules for exponents, those other laws of exponents are not actually essential for this particular unit and topic. One of the best ways for students to engage in the learning of this unit is to observe patterns. And that's how we'll start out our video. We're going to examine powers of 2 and powers of 4 and look for anything that we can use to create a rule. We would ask students to start by identifying places where the power of 2 is equal to the value of a power of 4 and highlighting it. For example, 2 squared is 4, and 4 to the first is 4. Likewise, 2 to the fourth is 16, 4 squared is 16, and so on. At this point, students may recognize that either the even powers of 2 are equivalent to a power of 4, or they may articulate that every other power of 2 is equivalent to a power of 4. For the moment, that's actually enough. If they can identify those patterns, we're set to figure out what the rules are. The best way to do that is to ask students to chart just those values and look for a pattern between the exponents. 2 squared is 4 to the first. 2 to the fourth is 4 squared. 2 to the sixth is 4 to the third, and so on. Students may notice at this point that there's a ratio that's formed with the exponents. The ratio is 2 to 1 or 1 to 2, depending on how you're reading the table. For every 1 power of 4, we double the equivalent exponent to get the power of 2. For every power of 2, we take half of it to get the equivalent power of 4. In other words, 2 to the 2x is the same as just 4 to the x. 2 to the x is the same as 4 to the 1/2 x. Let's go ahead and use this in a problem. In this problem, we have 2 to the x plus 3 equals 4 squared. We can't do anything with this problem as written. We can only solve these once there's an equivalent base. So we're going to have to change 4 into a base of 2. Now there's two different ways we could do this. We could simply say 4 squared is 2 to the 4th. Or we could use our power of powers rule. And that's what we'll do in this case, just to demonstrate. 2 to the x plus 3 equals 2 squared to the second power. Using our power of powers rule, that's equivalent to 2 to the 4th. We can now equate the exponents because the bases are the same. And notice that once we've equated our exponents, we're actually just solving a linear equation. Let's do another one, but this time let's look at powers of 2 and powers of 8. We'll ask students to do the same thing again. Identify places where there's a power of 2 with an equivalent value to a power of 8. 2 to the third, 8 to the first. 2 to the sixth, 8 squared, and so on through the table. Students may notice that instead of being every other one, it's now every third. This is going to be particularly important as we think about the pattern that will give us a rule. 2 to the third equals 8 to the first. 2 to the sixth, 8 to the second. 2 to the ninth, 8 to the third. When it was powers of 2 and powers of 4, there was a ratio of 2 to 1 or 1 to 2, depending on which way you were reading the powers. Here, it's not 2 to 1, it's 3 to 1, or 1 to 3, depending on which way we're reading the powers. For every 1 power of 8, we have 3 powers of 2. For every 3 powers of 2, we have 1 power of 8. That means that 2 to the 3x is the same as 8 to the x, or 2 to the x is the same as 8 to the 1/3 x. Let's go ahead and solve a problem. This particular task has a base of 4 and a base of 8. Well, we don't have any rule yet that equates those two, but we know that we can change both of those to powers of 2. So that's where we'll start. 4 is 2 to the second. 8 is 8 to the third, but 8 squared is just 2 to the sixth. Again, using that 3 to 1 ratio. At this point, I'm going to distribute using the power of powers rule for the expression on the left-hand side. I end up with 2 to the 2x plus 6 equals 2 to the sixth. I now have the same basis. I can equate the exponents. Notice at this point that the exponents form a linear equation and that the coefficient was formed from the exponent. Let's look at an extension possibility. We're going to combine both of these at once. We're going to use fractional powers to equate bases, and we're going to look at an equation where the resulting answer is either one solution, no solutions, or an infinite number of solutions. Let's start with looking at powers of 4 and powers of 8. And let's do the same exercise that we've been doing all throughout this activity. This is very interesting. Every third power of 4 is equivalent to every other power of 8. This is going to make a more interesting ratio. Before, it was 1 to 3, or 3 to 1, or 1 to 2, or 2 to 1. Here we have 3 to 2, or 2 to 3, and we can see that in the table that we're going to build. For every 3 powers of 4, we have 2 powers of 8. For every 2 powers of 8, we have 3 powers of 4. 4 to the 3 halves power is 8 to the first, or 4 to the first is 8 to the 2/3 power. This can be very challenging for students to grasp. It's a new concept, the idea of combining exponents with fractional values. Since it's new, let's take a look at this in another way. When I write 4 and I write 8 as products, 2 times 2 and 2 times 2 times 2, there's some interesting things that we can connect to those exponents. Notice that 8 has a third product of 2. When, when we look at that, it tells us that 8 is 3 of the 2 components that make 4, or 4 to the third 3 halves. Let's do the same thing, but with 4 and 8 going in the other direction. We can notice that 4 is 2 of the 3 equal products that make 8. Notice the missing product of 2. In other words, 4 is 2 of those 3 products, or 2/3 of the power of 8. This connection to why we have the fractional exponent is very useful. It also will connect later when students engage in square roots as powers of 1/2. Let's do the extension problem. Solve for x in the equation 4 to the 6x plus 12 equals 8 to the 4x plus 8. Here, I recognize that 4 is 2/3 of a power of 8, and so I'm going to just change that 4 to 8 to the 2/3 power. I now have the same base, and I can equate the exponents. I have a problem that requires some distributive property, so I'm going to go ahead and do that. This is interesting. When I come up with the distributive property, I see that I have an identity. 4x plus 8 equals 4x plus 8. It's the same. That means that for any value of x, I'm always going to have these two equal to each other. So there are an infinite number of solutions because x may be any value. Again, this is an extension that's not required for any of the assessments in Algebra 1, but it's a very valuable extension, especially if we're trying to deepen students' understanding and have them look for key relationships. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below. Thank you very much, and have a great day.